Hey guys, welcome to 8.3, 8.4 sections in the book on chemical bonding. Today we're going to be talking about covalent bonding. That's this one right here, the sharing of electrons. This is between nonmetals and nonmetals. So let's take a quick look. So covalent bonding happens because of a number of attractions, and the attractions are always in between negative and positive charges, like opposite sides of a magnet attract, opposite charges attract. Notice that the repulsions happens between the nucleus and nucleus of two atoms and the electrons between the two atoms, but the nucleus of one atom is also attracted to its own electrons, but also the electrons of other atoms. So this is how the bond actually happens, where the nucleus is attracted to the other atom's electrons. So the atoms stay in a relative distance, like close distance, away from each other. So it looks something like this. You see at the bottom here. So attractions between electrons and nuclei, and repulsions between electrons and repulsions between nuclei. Okay, so here's what happens though. Because atoms are different, that means that you can have like an unequal sharing of the electrons that are between them. Take a look at F2 at the example. The example here has both fluorine atoms pulling on the electrons the same amount because they're both the same kind of atom, which makes sense. So they both attract the electrons equally. But notice that hydrogen over here with the different colors, hydrogen on the left-hand side and fluorine on the right-hand side. Now, fluorine actually pulls on the electrons a lot harder than hydrogen does. And this property is called electronegativity. So fluorine has a much higher electronegativity than hydrogen does, which means that it pulls the electron from hydrogen closer to the fluorine and keeps it there, so that hydrogen has less negative density and fluorine has more negative density because of the fact that fluorine pulls harder. So it's almost like a tug of war between the two atoms, and fluorine definitely wins every time. Fluorine is the most electronegative atom that we have on the periodic table, so it always pulls the hardest. So you can see it says here, although atoms form compounds by sharing electrons, the electrons are not always equally shared. Fluorine pulls harder on the electrons as it shares the hydrogen than hydrogen does. Therefore, the fluorine end of the molecule has more electron density than the hydrogen end would. Okay, so let's take a quick look at electronegativity. On the left-hand side of the periodic table are where all the metals are, and they do not attract electrons very much at all. But as you go across, notice that it increases as you go across the periodic table from left to right, and notice that the smaller atoms pull harder on on electrons, which means that fluorine is by far the most electronegative atom. And then electronegativity decreases as you go down the chart. So this is electronegativity, and it's something we're going to use to show the difference between a polar covalent bond and a non-polar covalent bond. So when you have two atoms that are exactly the same, like two fluorines, even though they pull hard on the electrons, because it's two fluorines, they are pulling equally, which means that it's a non-polar bond, and we'll talk more about that later on. So let's keep moving. This is going to be a pretty quick one. So polar covalent. So let's talk specifics now. Let's quantify it. Let's give some numbers to it. When two atoms share electrons unequally, a bond dipole results. That means an unequal sharing of the charges. So when you have a more positive side and you have a more negative side. Now, of course, fluorine would fall over here in the more negative side because it pulls the electrons to itself, and hydrogen, of course, would fall over here in the more positive side. And the distance between the two of them then also has an effect. So if they're further apart, there's less of a dipole moment, and if they're closer together, there's more of a dipole moment, or something like that. I don't know. You see this right here? We're never going to use that equation. That's another equation that for what we're going to do doesn't matter that much to us. Okay, so let's take a look. Let's keep going. For polar covalent bonds, you see the bond length, you see the electron negativity difference, and then there's your dipole moment. Okay, so you can see that it looks like with bond length, the dipole moment increases. So you increase bond length, then the dipole moment increases also. So here we have situation. I'd have to take a look at that. Maybe not, maybe not. Maybe the bond length doesn't matter. My point is that the greater the difference in electronegativity, the more polar the bond is. Now, why does that matter? Well, it actually is the reason why water has the properties that it does, because there is a pretty significant difference in electronegativity. So it's a polar molecule, which then obviously changes its characteristics. Oh, okay, Lewis structures. That's it. We're finished. Hey, that was a quick 8.3, 8.4 notes. Excellent. I'll see you guys later.